Good afternoon, everybody. On behalf of all of us at Imperial College, I would like to warmly welcome you to the launch event for the Institute of Digital Molecular Design and Fabrication. We have a wonderful program ahead, and I would like, first of all, to do a bit of housekeeping before I will ask our provost to open the event officially. So this event is being recorded. You will have an opportunity to ask questions. Please do submit them with the Q&A facility on the right-hand side of the screen with the chat. Professor Mimi here will be reading out your questions. If you would not like your name to appear, please do post anonymously. And if we're not able to answer all the questions today, we will be answering them on our website, so we welcome your questions later as well. It is my honor to introduce our provost, Professor Ian Walmsley, FRS, who is also a professor of experimental physics here at Imperial, who will officially open the event right now for us. Thank you very much, Ian, and over to you.
Thank you, Sophia, and thank you to colleagues for the opportunity to participate in the launch of this very exciting new initiative. First, let me welcome all of our guests to this launch on behalf of the college. And then I would like to just turn to a bit of the context by which DigiFAB was initiated and has become an important strategic priority for the college. Next slide, please. Over the past couple of years, we have developed an academic strategy for the college. And the intention of this was to provide a cohesive vision for research, education and innovation, reaching across all areas of the college. And through this strategy, we focus on some areas of particular expertise that we already have, or areas that we want to build strengths in, and try and use those to identify and seize some of the emerging opportunities, both for new discovery and for new translation, that could have a major impact on understanding or answer big societal challenges. And the concept is that this will be made possible through a greater capacity and a greater capability engendered by working together across faculties and departments. The strategy is not only about research, of course, it's about enhancing our educational environment to prepare our students to be future leaders in these areas or in others, to innovate and to understand how to drive change. Further, it also aims to raise Imperial's profile as a world-leading research-intensive university so that we can continue to attract really bright staff and the best students to our programs and continue to deliver the sort of research impact that the college is known for. Next slide, please. So this is a cartoon, if you like, a diagram which indicates the broad structure of our academic strategy. Let me try and unpack it a bit for you. At the core are our academic disciplines, and that's built around the notion that science drives technology and technology enables science. And that symbiosis is underpinned by strength in disciplines, which can then work together in new ways to deliver new knowledge and new application. And the four central petals, if you like, indicate the things that are distinctive about the way in which Imperial goes about its research and education mission. So these are what we call our four capabilities, and they underpin our excellence. They're strengths that give us a unique position within the UK and allow us to build on the strategic themes that we focus on. Whilst the themes themselves may of course change over time, we think that these capabilities reflect excellence of activities that are really at the bedrock and really underpin what we do. And those are transdisciplinary, working of course across disciplines, sharing the ideas and expertise to change the world and to improve our understanding of it. We are quantitative as a STEM B institution. We have a very numbers-oriented approach to our work. We embrace all the possibilities of data and sophisticated statistics. Our expertise in these areas are used together with a qualitative inquiry to inform our approach to discovery and translation. We're committed to translating these ideas into new products, services, companies, advice and other to really deliver an impact from them. And we work closely with stakeholders, local and global communities, governments, industry, again, nationally and internationally, in order to ensure that our work is relevant, timely and accessible. And with those as the underpinning strengths, we identified collectively these 4 themes that form the outer ring here, which we seek to accelerate discovery and impact to society through college-wide investments in the immediate near-term future. And those 4 are: we help societies to become more sustainable by transforming manufacturing, attitudes to consumption and economic practices. We want to build a healthier society through new technologies and strategies that improve health services and support the prevention, diagnosis and treatment of disease. We enable discoveries and new technologies in artificial intelligence, machine learning, statistics, data science, robotics, and help to understand better how they will transform lives, environments, and to present and mitigate new challenges to the world of work. Next slide, please. Within that framework, we have now identified 5 initiatives that are currently underway, with others in the pipeline, into which we have built a framework of college support, both space, resources, and support for engagement. And those are the transition to zero pollution, just left to right here, the digital molecular design and fabrication, and the Institute of Infection, cross-faculty information technology initiative, and a program in deep tech entrepreneurship. So these 5 areas, these 5 themes, you can see contribute to the 4 outer petals of our academic strategy and build on our strength of disciplines at the core. Next slide, please. As noted, the Institute for Digital Molecular Design and Fabrication is one of the leading initiatives of our academic strategy, and I'm delighted for the college today to efficiently launch DigiFAB. It's a really fantastic example of the way in which we bring together expertise across all of our faculties. Of course, in DigiFAB, it's primarily in science and engineering, but also reaches across to medicine and entrepreneurship in the business school, with areas of AI, data analytics, automation, process engineering, which are brought together to transform molecular synthesis and materials development. Imperial's great strengths in these areas and historic strengths in these areas ensures that there's a real breadth and depth of talent to contribute to this initiative. And this multidisciplinary way of working is coupled with our unique infrastructure and the opportunities afforded by the new White City campus. And of course, the Molecular Sciences Research Hub is located in White City, so that we can work closely with business and other external partners and with the local community to provide an ecosystem for sector leadership that is not yet seen elsewhere. All of our academic strategy initiatives have the mission to benefit and improve society at their heart, and the aim of DigiFAB is also directed this to revolutionize the way we create new chemicals, materials, catalysts and medicine and agrochemicals at a scale and in a sustainable way, made possible by rapid advances in automation and machine learning. And of course, this has never been more pressing with current global challenges of climate change and the pandemic. The DigiFAB, of course, will work in collaboration with industry. It will foster entrepreneurship and contribute to the future of work. It will make an impact through education and through public engagement, training new generations of interdisciplinary scientists and engineers, and outreach to the community, and help to retrain professionals already engaged in these areas. With the college's great strengths in this area, our commitment to interdisciplinary research, our strong collaborations with industry, and the entrepreneurial spirit that I know the Department of Chemistry especially brings to all its activities, we're uniquely placed, I think, to deliver the vision of DigiFAB and to make a true impact on society. I look forward to seeing the success and the initiative go from strength to strength. Thank you all. Thank you, Sophia.
Thank you, Ian, very much for this introduction, and also for the support the college has given to DigiFAB. And it is my honor now and responsibility to tell you a little bit more on behalf of all our colleagues who are behind this project, what our vision is. So I am I'm Sofia Yadiraki. I'm the director of the Institute, and our vision is, as Ian already said, is to transform chemical design, discovery and fabrication by moving away from slow, labor-intensive manual methods to highly automated and data-driven approaches that capitalize about all the advances that we have made in AI, machine learning and data-rich approaches, so that we can deliver research innovation in diverse applications such as reaction optimization, AI-driven materials discovery, AI-driven drug discovery and precision agriculture. That are some of the big projects that are happening in the college that contribute towards our healthy, sustainable and smart society. Another major aim of DigiFAB is in that of training. It's extremely important for us to deliver the new generation of scientists who are able to innovate in this area, but also to help anyone who's interested in changing their skills throughout their careers. We're really committed to help with the future of work and the quality of work, as well as working with the local community and starting with outreach from the school level all the way to very advanced levels as well. Why this is happening now? In fact, we started before the pandemic, but of course, like everybody else, if anything, we've seen that this is a very important time, but we need to accelerate our efforts in this area. Discovering and developing chemicals with desired properties, whether these are medicinal materials or agrochemicals, is a very slow and expensive process. We have benefited from advances in this area. However, it is taking longer and usually is more expensive for example, for a drug to go from discovery to market. And this is counterintuitive, but it usually takes more than a decade and $1 billion to get to that point. And if anything, the past year has brought to us all to the fore that we need to, we can no longer accept such timescales. I'm going to give a particular example only because we are at Imperial College, and this is at the heart of where antibiotics, in some sense, started with the discovery in the 20s of penicillin, where we have for 100 years benefited from a wealth of classes of antibiotics that have really improved our quality of life. However, the last 30 years has seen what is now called the discovery void. We have not had any new classes or much slower classes of antibiotics. The chemical space that we're accessing has really shrunk. And that has been coupled with the opposite, a very big increase in antibiotic resistance. So the two things together are making this a very, very real demand for us to look for new chemical space, since this resistance is fast outpacing our discovery. And I would like to talk a little bit about what the challenges are in exploring this molecular space. First and foremost, of course, is that of scale. Sometimes we don't think about it, and this vast number of 10 to the 60 is only an estimate that a lot of people bring out about the possible molecules we could be creating. It's bigger than the atoms we have in our solar system. We have only explored a very, very tiny part of it. Even with all the terrific advances we're doing in our high throughput technologies, we are only sampling a very, very small part of it. And even more important, something that again sometimes gets not discussed, is that there is this issue of complexity, what our colleagues in maths or statistics sometimes call the curse of dimensionality. These are very high dimensional systems. We are interested in a lot of different properties, and we're trying to concentrate on only a few, depending on the scale or resolution of what we're interested in. That makes our problem much harder to address or to solve. And sometimes, particularly so in chemistry, sometimes we like to use this idea of landscapes, and you see that people talking about throwing ropes in the mountains in the dark when we try to explore those landscapes. But what we're actually talking about is all the difficulty we've had in doing so. However, here at DigiFAB, we want to take this challenge as an opportunity to do things differently. And by, again, taking into advances all the innovation we're doing in this area, we want to capitalize on all the data that has been available and is often not used in these areas, and use all these new approaches we have developed in exploring this chemical space, first and foremost through new algorithms, optimization, as well as new chemical representations that allow us to do this differently. Through to our automated lab platforms, we are very fortunate to have a variety of such platforms here, and we are continuing to innovate in that area, together with high throughput characterization that allows us to analyze the generated data that we get. And of course, the whole point of the whole point of this is to be able to synthesize what it is that we're interested in at the right scale, whether this is at a low cost 3D printer for individual use, or at a big manufacturing scale that goes at production at the same time. So we really want and aspire to close this loop, and the loop doesn't only go forward, it also goes backward and across. And we are tapping into the expertise that we have across the college in chemistry and chemical engineering, physics, and all other disciplines that are helping us innovate in these areas, but more importantly, by working together so that we are able to actually close this loop and innovate in a way that Imperial is always good at for interdisciplinary research. We are, of course, you see everywhere all of this, the word data. The whole research cycle is underpinned by data. And so, of course, AI and machine learning cannot be done without good quality and representative data. This is extremely important in the chemical sciences because unlike other areas, there is very poor data or no data or irreproducible data. So a very important part of our strategy, and where we think it's also an ethical component, perhaps not in the way that it works for other socioeconomic problems, but for us, it is one of equal access of this data, and above all, reproducibility. So it's not just about big data, but it is about good data that we are committed to working with introducing electronic lab books and other good practices, and working with the international community to make this a reality as well. Behind us is expertise from all departments. We have also experts from AI and statistics and computing, maths, the life sciences and the business school for how to incorporate digital transformation in working environments. This is very important for us, as well as working with the advanced hackspace. Imperial is a very unique place. We can actually allow innovation from the bottom up. Our students can try out ideas and work with the local community as well. And more importantly, we have all this multidisciplinary expertise from centers that are around this area where benefit and we learn from and for the AI part, whether it is in the lab and in robotics, or whether it is in our algorithmic approaches, or whether it's a combination of both, as well as the applications that we are interested in. We are fortunate to host the Automation Center on behalf of the country, for the Center for Rapid Online Analysis, that gives access to lots of high throughput experimentation and loads of automated in-flow reactions, as well as on-the-fly analysis, which of course allows us to have a great facility, coupled with other labs that are within DigiFAB innovating with different technologies, and you will hear more about this in the talk later. We're also very lucky to have the new White City campus here at Imperial, which is not only the wonderful buildings, but also the community around us that is very much focused on innovation, entrepreneurship, and also working with our local community and local government. That is very important to us. Some of the challenges we are working on to start with are, of course, in the optimization of synthetic routes. These are quite important for, of course, not only faster, but also and cheaper, but also greener and sustainable ways to solve the chemical problems in reactions we're interested in. And we're going to hear from our keynote speaker about the way he started and is continuing to make fantastic advances in that area. We are also very much working on materials discovery and many different materials, from graphene and 2D materials in flexible electronics and smart textiles that are used in wearables and are used in healthcare applications, but also porous materials that are very important in sustainability. And we're going to hear a talk on this just after a bit later. We are also committed in looking at exploring new chemical space, whether it is for drug discovery or agrochemicals. And in here, we're taking different approaches and focusing on new representations of molecules that can be used in machine learning algorithms. One of the big areas here is 3D representations. And we are looking for allosteric repurposing and antibody discoveries, but above all, very much into different representations as well. So, in materials discovery are very important for sustainable separations. As I said, Becky and Kim would later give you the details of how they are doing this fantastic work together, where data and automation are working in a cycle to innovate in this area, which are, of course, very important for world's energy problems. I will give you another example from chemical engineers, part of our program. Here, a slightly different approach, which again in the sustainable separation. Here, we have the big problem of how to choose of all the many absorbents that may be available and are increasingly coming into the fore. As I said, we don't have time to look for all of them, but more importantly, we want to design before we start the experimental process, not only in the molecular properties, but also in the macroscopic process itself. So I think this is a quite important approach of designing at the microscopic and the macroscopic level. And this is where working together of the different disciplines come in to allow us to close this loop, first through our approach in design, but also optimization. We have one of the world-class optimization groups at Imperial to start the process, and then use automation. A different platform here, part of the Atlas group. We are very fortunate to be part of and host and see how this would lead, so that we are actually able to make this a reality. I said that not only research, but training is extremely important for us, especially because these scientists or people who can operate in these boundaries are not easy to find and very much in need. So we have been committed very much into this. We started a doctoral training program a year ago, and you see the picture before COVID. This was allowed to happen. We have another one in automation in the life sciences, and we are extremely excited to start a brand new MSc degree in digital chemistry in October, which will be both available online and for people who want to come on campus, and will be available as part-time for anybody who may wish to take it as retraining as well. Giving access and motivating our students from the beginning all the way to advance their career is important to us. And we are organizing events like datathons. We had great success with this, where we asked the students, anybody who wanted to enter from Imperial actually, to work in teams to predict how a molecule packs in the solid state. And this was a fully online event on GatherTown that was a great success and showed how our students and early career researchers can work together from all the disciplines to solve in such problems. We are very much committed to in this hackathon idea and creating a chemical hack space that will be dedicated to problems related to digital molecular design. And we have this summer a challenge where we are hoping teams will try to build automated but low-cost liquid handling platforms and turbidimeters so that they are able to integrate them together. we hope that these kind of activities, we will open them up to high school students and anybody interested in the local community as well. This is a new area and we want to be connected with all the top people around to advise us, not only in the UK, but also internationally, and very much also staying close with industry, whether it is big companies that are innovating in this area or smaller companies that are actually at the forefront of these approaches. We are also part of a global network in this area that has just been formed, and we are incredibly proud to be part of that as well, as a commitment of what is there to come. We want to have an impact in society, so of course we have to work, and we are already working with SMEs, industry and the local government. We are co-creating projects, whether for our doctoral training center or for big projects and big ideas as well. And we are putting together a business club for all the companies that are interested in this exchange of ideas and working with us. And that's an important part of what we want to do. And finally, I would like to end by saying that this, of course, started as the dialer molecule network made a vision for the next 40 years for creating such a digital molecule, as we were saying. And when we opened a building here at White City, we held the Chemistry Futures event, which again projected advances in many years ahead. And even over the pandemic, the Royal Society of Chemistry released its national call for the digital futures that are very much in alignment with DigiFAB's vision. And I hope I convinced you that actually this future is now, and that especially after the winter we've had, I would like to end by quoting one of my favorite poems, Amos Heaney, who said that if we can winter this one out, we can summer anywhere. So I'm hoping that you agree that the future is a bright one. Before thanking you very much for your attention, I would like to thank everybody in DigiFAB who is helping articulating this vision and making it real, as well as our manager, Dr. Fang Li, who joined us in November and is part of our journey. So thank you very much.
Okay, Sophia, thank you very much for that lovely presentation. We have time for some questions. So there's been a few things coming in the Q&A, which I'm moderating. So I think what I'll do is combine two questions into one. So before today's meeting, I got a question on what you think, how do students and junior researchers, early career researchers prepare to work in an interdisciplinary field like this? I mean, with chemistry, data science, material on one end. And then on the other hand, we have Stephen Boxall, which asks a question on how then we work with business, UK businesses, to deliver value and sustainability and all that to the UK community. Do you want to comment on that?
Yes, absolutely. So I hope we are by creating all these new courses that are truly interdisciplinary, we are allowing the people who are really interested to do this training that they require. For example, in our courses that we teach data analytics, automation in the lab, as well as chemical synthesis. So we are allowing people to work together in this way. And also by all these events that we are putting together, like the datathons and hackathons, we're giving people the taste of what it is to work with others. We were extremely proud in our datathon that we had teams participating from all disciplines, and actually we had winners from maths, physics or chemistry, which shows us that actually our students are becoming more and more. So So I think working very closely with industries is very important. Industry has also making similar innovations on their side, and I think working together to make sure that we learn where they are innovating and they learn from new approaches we have is key. I think we can create value in, for example, using data that has been sitting there that has not been used or reused. We can really help in creating more efficient workflows and allowing people to actually innovate and use their expertise instead of tedious and repetitive approaches into more creative and new things that they can do. So I think that's definitely the case. So instead of, I think, feeling afraid that these kind of approaches will take jobs away, I think we want to show that it is actually the opposite, that they will create better quality work for people. And that's where training and continuous training is very important.
I couldn't agree more. I'm just looking at the time, Sophia. We have 2 minutes before Alex. Would you like to take another question? Or?
Yeah, of course. Yeah, one more.
Okay, so I'll choose a short one. So there's a question here from Anonymous. So somebody has a question about managing data. How are we going to manage all this cross interdisciplinary data? I think you touched on that briefly. Maybe you want to just quickly, yeah.
Yes, it is a big challenge, but we have a big committee of people working on this. We have expertise actually at Imperial for this. It is also a difficult problem because every discipline has its own structures. And I'm hoping here we can learn actually from one of our leads who has managed this for the high energy physics at CERN, that will teach us how to bring the communities together. So please do keep your eyes on us, and I hope we'll be able to make some progress on this in the time ahead.
I think that's it. I think, yeah, we're ready to move on. I think it's 10 past.
Okay, perfect. Thank you, Mimi, and thank you everyone for your attention again. I cannot see you, but I hope you're there. It's my pleasure now to introduce Dr. Alex Brunskov, who is Head of Advanced Materials at EPSRC. As you have seen, a lot of or most of our work is generously funded by EPSRC, and we rely very much in the support for this to continue to innovate. I think Alex is a great speaker, not only because he's head of advanced materials, but because he has helped bring together 3 interdisciplinary institutes funded by EPSRC before. So we are very, very keen to hear what he has to say, and thank you very much for being with us. Alex, all for you.
Hi everyone. So hopefully you can see my slides now. Just to, I guess, to introduce myself, I'm Alex Brunskov. I am Head of Advanced Materials at EPSRC, and I guess I'm very happy to be here today. And what I'm going to talk about is, I guess, quite a general, high level, both around kind of the UK research funding landscape, the layout within which EPSRC operates, and then I'll kind of move on towards talking a little bit more about kind of how EPSRC itself underpins and supports advanced materials research and the ways in which it goes about it. So just to kind of initially run over what I imagine quite a few of you are already aware, EPSRC is part of what we call UK Research and Innovation. This was developed or established in April 2018, and it very much brings together all of the research councils, so the 7 research councils that previously existed, along with Research England and Innovate UK. And then if you think about how the landscape within which UKRI operates, it's a much more wide scientific community, which involves kind of all of the universities, businesses, institutes and charities, and then some of the other kind of devolved administrations. And in terms of like the hierarchy within UKRI, we sit under BASE, so our funding directly comes from government, although we aren't a government department ourselves. So I just want to go very quickly over kind of the UK research and innovation kind of vision and mission, and it's really quite high level. So really thinking about establishing an outstanding research and innovation system in the UK that gives everyone the opportunity to contribute and kind of cause societal benefit. And really, in order to do this, kind of the UKRI mission is talking about convening and catalyzing and investing to really create that thriving, inclusive research base that allows public good and prosperity to come from scientific research. So if you move on to kind of thinking more about EPSRC, where I actually kind of fundamentally sit, in 2019 we announced a delivery plan which was related to kind of how we wanted to support our research base, and we set it out in a number of different levels. So the 3 levels here, effectively the first level, which is the productive, connected, healthy and resilient nations, they very much highlight the kind of outcomes we're looking to achieve by funding research and research infrastructure across the UK. And then the other 2 levels that we have are very much on the kind of the realizing the potential of the physical sciences and engineering research base that we have within the UK. And then, so that's the kind of supporting excellent research, supporting excellent people. But then equally, we have the other level, which is supporting the environment within which those people sit. So thinking about the research infrastructure that's actually required to enable that excellent science to take place. In terms of EPSRC's vision, it's very much thinking about establishing the UK as a world-leading engineering and physical sciences base, and working within the kind of ecosystem that I've described, and with kind of external partners to deliver kind of societal benefit and economic impact from that research base. And in order to do that, one of the things that we've been aiming to achieve is thinking about our partnerships, working with business to actually allow us to meet some of the government targets that have been set out. So how do we do that? One of the things that we really need to do in order to kind of achieve our vision is think about how we can engage effectively with the research community and other partners. Really think about working effectively with them to learn and understand kind of what's required within lots of different areas with which we fund, and really then position that to highlight to government, for example, why they should invest in certain areas. A lot of it will be around that kind of effectively articulating what the future portfolio needs are and what directions the UK should be going with in terms of funding. And quite often, I guess the last bullet point here is talking about the fact that we often have to reply to kind of government requests on short term. A lot of the things that we need to respond to happen at kind of very short notice, and therefore we have to kind of plan ahead and think about the types of areas in advance so that we're on the front foot when it comes to those types of things. So that's kind of the general kind of background that I was going to run through. In terms of the next few slides, what I'm going to look is just highlighting a few areas in which EPSRC supports materials. And it's really not designed to show you a massive depth of what we support, but really thinking about the kind of different types of investments we make and the different areas that funding comes through in terms of what themes within EPSRC itself and how we work. So if I just run through some of them, like form, which you can see on this slide. This is an engineering program grant. Program grants are one of the major types of investments that EPSRC makes. They're very much kind of flagship major research investments. It's focused around kind of developing lightweight alloys for sustainable transport. And it's funded through, as I mentioned, the engineering theme within EPSRC, which is one of our capability themes, and has one of our largest budgets. It's really focused on kind of engineering the microstructure to develop lightweight and cost-effective systems in the UK, and for transport systems is one of the major focuses. So if we think about some of the other investments that we make across the UK, one of the things that our manufacturing theme does is invest in what we call our future manufacturing research hubs. Now, there are 11 hubs across the UK, and these are very much focused around actually developing early stage research, but enabling that research to then be driven towards kind of the long-term industrial challenges within which it sits, and really thinking about kind of accessing that research and transporting it into the kind of impact domain. 7 of the hubs kind of in a way support advanced materials research, which equates to around 71 million. And it's just kind of a different aspect of the type of research we fund, and also it comes through another different source of the manufacturing theme. One of the things that our physical sciences theme actually supports is the UK Metamaterials Network. Now, this is based in Exeter University, but it very much works with links to Innovate UK and the knowledge transfer networks. So there is also investment in a metamaterials knowledge transfer network, and working together with the network investment that we've made, they're very much looking to kind of develop on the fact that the UK has been in the past, or it still is in areas, kind of a leader in development of metamaterials. But it's thinking about kind of how we can try and maintain that existing level and really capitalize on some of our existing skills. There is another kind of aspect to our funding, which is much more central, and one of the major investments that we've made over recent years was in the Henry Royce Institute. Now, we got additional funding to set up the Henry Royce Institute, which is very much focused around advanced materials, as you can see here. Advanced Materials Institute is kind of its initial funding was around 235 million. It was announced in 2014, but it wasn't due to be fully operational until 2021. So it's just coming fully online now. It initially was, I guess there were things that came online across different periods of time. So there are a number of kind of investments that have been made across the UK. The hub itself is in Manchester, but there are a number of different university partners involved. And it offers both an array of different kind of facilities that the UK research base is allowed to access and use. But equally, it does then have some kind of challenge focuses itself. And it's really thinking about convening the materials community and working with the materials community in order to feed in information about kind of key areas, key topics that we might be able to invest in the future. They've thought about kind of how they present themselves, and they very much move towards kind of the output focus rather than kind of specific areas of research wise. And as you can see from the slide, they're very much focused around kind of materials for a sustainable society. So that's kind of a brief whistle-stop tour of some of the investments we make. In terms of what we would class our advanced materials portfolio, we effectively invest, at any one time it obviously fluctuates, but current figures from kind of January, we are investing in 432 kind of awards that are relevant to advanced materials, equating to effectively £450 million, and across a wide array of institutions. And as you can see from the map, there are kind of a breakdown of where those investments are made. There's also a number of different centres for doctoral training that we've invested in, equating to around 174 million. They aren't all specifically materials focused, but they all have elements of advanced materials work within them. And then there are a range of other investments, such as the Henry Royce Institute, the advanced computing facilities such as Archer 2, and some other national facilities. So the final kind of area that I wanted to cover in my talk was really focusing in on the advanced materials theme within EPSRC, which is actually my specific role. So what we've been doing internally in the recent year or so is really identifying what we want to achieve as a theme within EPSRC, because previously we haven't had an advanced materials theme. It's very much been split around. Advanced materials has been supported through the other themes, so physical sciences, engineering, maths, ICT. And we are now putting together kind of our plans. This is just to highlight kind of our mission statement. So what we're really looking to do is convene and catalyze the very multidisciplinary community that exists across the materials space, because it inputs into so many different areas. In terms of kind of thinking about it, it's advanced materials in our kind of definition. We're thinking about novel and optimized materials, and we're thinking about them being enablers for sustainable futures, and addressing challenges, things such as net zero, and enhancing our economic prosperity. In terms of the vision around that, what we really want to see in terms of EPSRC is us as part of UKRI being seen as a key partner with the materials community, really taking on that leadership role and helping the community scope, develop and champion the materials research that the UK can offer, and where it will really provide impact. In terms of the layout of the team, I'm afraid I haven't actually updated all of the names. So Claire Spooner is was head of advanced materials until recently. So I am now head of advanced materials. There's another senior portfolio manager in our team currently, who's Jan Taylor, and there is another vacant spot currently. This is just really to show kind of the fact that advanced materials is extremely pervasive across EPSRC. So our role isn't to be a core funder of research. A lot of the funding is dealt with within the existing themes, which you can see at the bottom. But what we are trying to do as a team is work across all of those themes, and by working across those themes, identify areas that are of interest, areas that are kind of emerging technology areas which we might be able to work with other partners across EPSRC or wider, be it business, government, other research communities, cross councils, and really identify those challenge areas where we might be able to capitalize on either our strength or the fact that it addresses different challenges, and therefore we can make cases to government for additional funding within advanced materials. So in terms of the kind of strategic focus that we've put together, we've got a number of different theme aims, so I won't go into details around most of them, but it's really thinking about raising the profile of materials within the UK, especially reflecting it back to government and the importance of investment in these types of areas, thinking about securing future funding, future generations of researchers, and one of the key kind of outputs that we're looking for is thinking about kind of reducing the really long timescales you tend to see for materials innovation to use, and thinking about kind of how we can do that by creating some sort of unified strategy across the community. Initially, we're thinking about kind of how we identify what we want to achieve within EPSRC, and the current layout that we've got is thinking about kind of materials for a sustainable future, so it very much aligns to what I mentioned in the Royce Institute. And then thinking about a number of different cross-cutting priorities, so thinking about the skills base that we need, the research infrastructure that's required, the types of outputs and international kind of partnerships. And then down the bottom of this, we've got kind of the different research priorities, where we're talking about kind of fundamental research, kind of mission-inspired and translational aspects. Now, these obviously all interact in a number of different ways, and we wouldn't expect things to be solidly within a box, within the research challenges. They obviously cross the different scales, but it's just kind of the way we're framing it. And then within that research challenge strategy, we're thinking about there being other cross-cutting research priorities, which is kind of the materials characterization, digital materials development, and aspects of that type. The emerging technologies part on here is really reflecting the fact that there are government drivers that we need to work within and towards, and emerging technologies is one of the things that government are very interested in currently. This is just a wider view of some of the work we've been doing, and actually some of the areas that have been brought up. I won't run through them, and they're not really designed for you to read right now, but it's really to show kind of some of the areas that we're developing across EPSRC and wider under that research kind of heading of fundamental, mission-inspired and translational. And these are some of the kind of areas that we've actually initially started scoping up. Some of these are further along than others, and they kind of give, and they come from different routes. So the materials for quantum stuff has become interesting from working with the PS community, but also the quantum theme within the EPSRC. So that's quite an internal one, whereas other ones we've had are advisory groups. So materials for health is very much working across UKRI. And thinking about tackling infections, which obviously from the current environment has had quite a lot of interest. And it's working with our kind of materials advisory stream. Some of the other ones we've got here are, they come from different routes. So corrosion and degradation has come out of some work with kind of industrial partners and interest to them. Critical material supplies is working across the research councils. One of the final kind of things I wanted to mention is kind of what we need to achieve working with the community is really thinking about how we can influence government and articulate the value of materials. And by doing so, we can hopefully achieve kind of great things in terms of getting additional funding into the area. A number of the different kind of strategies and types of things we have to think about how we align to. So thinking about the UK R&D roadmap, the integrated review, and so on. And then what I would really just kind of highlight now is that we really want to work with the materials community in its broadest sense, and really think about what are the big new ideas that we can talk about. How can EPSRC develop the steady pipeline of ideas so that we can really capitalize when we get opportunities to feed things into government? And how can we really deliver the proactive kind of vibrant community that we're looking for? And I'm going to finish there, I think. So if I stop sharing.
So, Alex, would you be happy to take some questions?
Yeah, that's okay.
That's okay, Sophia? Yeah. So there's two questions that came in during your talk. I think it's in the context of the manufacturing, futures manufacturing hub.
Okay.
So the first question is from Steve Boxall again, about economic impact. You know, how do you ensure that the economic benefits are equitably distributed and not just, you know, limited to the companies that you're working with these research hubs? Okay,
I mean, so on that sense, I think although we talk about the kind of developing the translation of the research towards industrial impact, it's very much kind of thinking about creating hubs around types of areas of research and kind of then bringing in industrial partners. By creating that kind of critical mass, it allows them to attract kind of a number of different industrial partners. So it really kind of broadens out the kind of impact that you can achieve.
Yep. I think that's okay, Sophia. Is it?
Thank you. Yeah, thank you very much, Alex, for this, for your presentation and the landscape, and gladly to see that digital materials is there at the heart of things. Again, thank you so much. Welcome back, everybody. Thank you for being with us, and it is my absolute pleasure to introduce now our keynote speaker, Professor Lee Cronin, who is the Regius Professor of Chemistry at Glasgow. Lee is a pioneer in this area, in the several research areas that are truly interdisciplinary, but in particular the digitization of chemistry and AI approaches to synthesis and chemistry in general. And we're really looking forward to his presentation right now on universal synthesis machines and computation.
Great. So it's a pleasure to be here. I must say that when I first heard of the initiative that Imperial was starting, I was really excited because I think there are so many interesting research groups and new ideas coming together. It was really great to see what's going on, to support you guys, and also share with you a little bit of what we're trying to do in digital chemistry in Glasgow. So I'm just going to transition onto my first slide and see if the transition works, and if it works, then we're good. So the mission of the lab in Glasgow, the reason why we started doing digital chemistry actually is because we were interested in basically exploring the origin of life and developing new life forms. May seem a bit far away from digital materials, but I'll explain as we go on. Secondly, we're interested in the digitization of chemistry because in pursuing this idea of looking for new life forms, we realized we had to automate chemistry, or at least try to. I must say I started this over a decade ago, and I feel like I'm getting younger every day, but of course there are many great young people out there. But a decade ago, lots of people dismissed this as just some kind of weird fantasy that we didn't have the computing power or the robotic power or the ability to do chemistry automatically, because it was so difficult. The other thing that we're interested in doing from this is kind of building chemical computers. If we can use robotics to do synthesis, then it seems appropriate to ask the question, can we use chemistry to do computation? In fact, how does the brain work? And finally, we're interested in transition to information. But let me focus on what we've been doing in Glasgow in terms of defining the field of digital chemistry along with others. And we've heard some really great talks today. I really like the digital material stuff and the evolutionary, exploring evolutionary material space. I think that's really great. So the thing is, if we want to start to digitize chemistry or to make chemistry easier to look in big data, then we need to understand the data collection process. And I would say at the beginning, there was lots of cultural resistance because people would suggest that we were trying to replace the chemist, and far from it. The chemist and the material scientist and the formulator and the nanomaterials person are center of this idea. What we want to try and do is to make the process more reproducible and also to make it traceable. So what we have right now is this whole written procedure, user interpretation. It's all manual, kind of analog, bespoke, like a Michelin star chef. Some organic chemists are probably better than Michelin star chefs. We're not allowed to eat the molecules anymore. Probably that's a good thing. but some of the chemistry that's done and some of that tacit knowledge is really important to some groups and doesn't always come across. So there's this classic problem of going from the current to a more digitized process where we might have a procedural code, a hardware graph, we will compile and get a result and we could adapt. And this is much more transparent. You have a code you can edit, you have a series of version control systems. You can share with students and experts, and maybe expert will say, oh, you used the wrong catalyst or the wrong temperature or the wrong type of surface area to volume ratio. So the idea of getting this digitization isn't about automation to replace the chemist. It's about reproducibility and getting access to chemical space. And I think a lot of the talks today have introduced this idea really well. I would compare this to what we're doing with this kind of bespoke machinery, say in chemistry right now, in DNA synthesis, peptide synthesis, or carbohydrate synthesis, to be similar to what we have in these single class computing machines. Chemistry is already automated. In fact, if it wasn't for the automation of RNA synthesis and DNA synthesis, we wouldn't have a vaccine right now. So for the COVID-19, so that's already well established. So what am I meaning here? Well, I think that it's always good to start a new intersection between two disciplines with Hello World. Lots of the computer scientists, when they were developing programming languages, the first thing they would get their program to do is say Hello World. And to do this, originally on the first kind of mainframes, you'd have a punch card where you literally punched in the designation, the holes, so you could spell this Hello World. If you were going to write it in assembly, you would be able to write poke the letters into memory and then display the memory. If you're writing in Python, say print hello world, hello world. So you have these levels of abstraction that materials science, and in particular organic synthesis, already actually has. The process of retrosynthetic analysis is the most beautiful abstraction system that was developed by organic chemists many years ago, and it's been used with great efficiency. The problem is there's not a hard connection between the requirements to do that synthesis and the concept of coming up with those connections. So lots of people kind of think that there is a kind of break between those two things. So what we're trying to do in my lab, and we've been doing, like I say, for about a decade, is trying to make a programming language for material science and chemistry, and actually also synthetic biology. And I remember years ago when I wandered into the lab and I said, right guys, I can never reproduce anything you guys do, or you can't reproduce each other. We're all going to start to adhere to this protocol. And the postdocs just kicked me out. They said, no, this is a very silly idea. Why are you making us adhere to a language that when we're doing all this manual work? So I went back the next day and said, hey guys, can we build some really cool robots to look at the most tedious things you do? You know, maybe some reactions, some additions, crystallizations. So we started to make what we call the Chemputer, where we have this universal actions. It works on any robot. It's human and machine readable. And we have an approach that basically allows you to verify and reproduce your unit operations. It really is nothing more than chemical and materials engineering, if you like, but in the fume hood. So to do this, we started to build this idea of this chemical state machine. And this chemical state machine, we found out very quickly, like a Turing machine, computation is only computation if you can put in a program and run reliably on the hardware that's qualified each time. So computation is the process of running the code on any reliable, compatible hardware every time. So I'm going to explain what that means and what the power is. We need to have a scheduler and a graph. And if this all seems a bit complicated, a bit too computer sciencey, don't worry. It's really very simple. What we have to do is make a language which is basically expressible in English or Mandarin or French or whatever your favorite language is in prose that gets translated into an abstraction that then can be compiled on a robot. And we've managed to do this with a code called KDL. In fact, it would take the average person probably watching this lecture now no more than 1 hour to be fully proficient in every single aspect of KDL. It is easier than learning how to fill out a lab book. And later on this month, this language is going to be released for free to the world. So it compiles on a robot and you can run all sorts of chemistry. So let me give you an example. One of the first examples we published a few years ago where we took the first computer idea, we built this based around the batched chemistry. So it uses existing hardware, existing glassware. You'll see a round bottom flask in there, a stirrer, a rotary evaporator. The only thing that really we built was a few pumps and valves you can see in the background. And these pumps and valves interpret the English via the KDL and do the reaction. You can see the reactions just happened. It's now going to the separator, and then at the separation it goes to the rotary evaporator, and then we will then isolate the material. And you can see that we've taken the solvent out, so we can even audit the solvent. So we can count in the amount of solvent that we put into the system and take out and reuse. So we have an interesting circular economy here. And then we can then present the material at the end on the left-hand side here in our chiller and present the product. Okay, so what we just did there is we were able not just to make one molecule on that machine, but basically we can make any molecule on that machine that you can make by hand in a chemical laboratory. And we've been spending the last 3 years explaining how this might work. So there's a couple of examples here where we've done a cross-coupling reaction, peptide synthesis, and this making this diazarine, which are quite expensive and unstable molecules. And the idea is to show that just by tweaking the code, we add in the reagents and the computer will run in a loop, as long as you know how the synthesis works. So you need to have done it by hand typically before. So as long as you've done it once by hand, you can then write the code in KDL and run it. And this is quite exciting because this then takes a lot of the effort out of reproducing chemistry you've done. You don't need to do a new reaction more than once or twice by hand. That was the idea. So we've also expanded all this chemistry here. We've now done about 100 different reactions on the computer right now, different reactions, and made libraries and molecules and done up to 12-step syntheses. We've also working on installing up to 4 chiral centers and making a natural product and making libraries and natural products, and also made a random number generator using the soy reaction and a computer, which is kind of cool because I think, as we're going to hear later, chiral water catalysis is extremely interesting mechanistically, and there's lots of scope for exploring how we can install and also look at diversity in chemical space, particularly if we're going further into chemical space than we have before. So the kind of modules we've made in the system, there's lots of them, photochemical modules, high throughput modules, but the important thing to understand is these aren't just random robots, very expensive. They were built by hand by my group, just by using a 3D printer and a few basic electronics. The language is really most important. So any hardware that you have that you've bought, you can qualify. And I can see up there in the top left corner, you can see our Schlenkline computer that we built the other week. And now we use a series of the language to control these vacuum taps, and we can do really quite sophisticated and very reactive chemistry. But what beyond, we have this language, but is it restricted to organic synthesis? Well, no, we can also use the same language to make nanoparticles. As we can see here, we've got a description of how we might make a gold nanoparticles and then use a measurement space and a feature space to then use UV visible spectroscopy to give us feedback to try and hone in and make the best particles. And then at the end, once we've gone through our algorithm, in this case it's a MapElite's algorithm, we can do this chemistry in real time and make a whole series of new nanoparticles. And all these particles you see on the bottom right corner here, faceted particles are made in a robot, layer by layer, facet by facet. And if you go down to, say, the one on the bottom here, the L3-6 or L3-5, there is a code for this and a KDL, which you can then run in any qualified robot. And I think that's kind of cool because that means then if you have the right hardware, which should be simple, you should be able to take the code and check what we're telling you really works. So what about also the autonomous discovery of energy materials as a good example? So I said to my team, okay, well, let's go now from a workflow to make, say, a supercapacitor. Let's say in this case we want to make a tungsten oxide, to dope it in with some vanidates and see if we can make polyoxymalate type material as a function of pH and reduction, and see if we can make something as electrochemically interesting. So what we did first of all was build this flow diagram of the inputs. You know, here are the top left corner, what you're going to add in, then the unit operation, and then the measurement, and then basically the processing, and then the electrochemical analysis. This is the robot we dreamed of making, because we already have these modules in our group already using the language. The language tells us what to build. It's a bit like once you learn the language, you know what paragraphs you can write, and you know what verses if you view it like poetry or something. So it's very important to think about the modules in the same way the IBM PC that we now use, or the clones now, have a well-defined specification for the RAM and the CPU and the hard disk and the buses. That type of process laterally leads itself to the language. So we built this little robot here, again in the lab, just hacked it together. I'm sure that you guys in your hack space will be able to, Imperial will be able to do things like this, if not doing it already. Be surprised if not. And then here's a picture of the robot working. And not only is the robot doing the reactions, measuring the pH, we're also on the left-hand side. On the right-hand side, you're going to see the electrochemical probe go in a moment and do the electrochemistry and do thin film chemistry and measure the material. And we've been making some relatively decent capacitors. So this all started years ago for making an evolutionary engine. Part of this slide seems to have disappeared, but it doesn't matter. I can explain how it works. The idea is that we wanted to evolve droplets in real time, in real space, because we didn't have enough computational power to simulate them. So the idea was to build a robot that would literally make a Westworld for droplets, if you guys know the series, and then allow the droplets to fight it out in an environment and then select them to live or die. And where the patterns are gone, the fluidic devices are kind of missing, but you have this kind of life cycle of droplets. And in the top right corner, you can see again, using the KDL, we were able to add our formulations, and using computer vision and an evolutionary algorithm, we evolved these droplets in populations. We were able to show that we could develop really kind of weird behaviors in the formulation space, be it droplets that would just explode, or droplets that would get connected, or droplets that were wobbling, or even droplets that would just spontaneously after a few minutes dissolve. And what we're trying to do right now is actually do combinatorial chemistry in these droplets as a function of the way they interact with one another. A bit like, you know, maybe like DNA bar-coded small molecules, but a little bit more crazy, because the actual outcome would be a result of the collision between the droplets, which would be rather stochastic. And there's just an example here of how the different droplets can be videoed, and you can look at the dynamics on the inside of the droplet on the left-hand side. And by collecting the data and using an evolutionary algorithm, very similar to the type of algorithm that was mentioned before, but this algorithm now is occurring in real space, like in a real ecosystem where the droplets were interacting. The population of droplets are physical entities in the dish rather than in a simulation or in a computer memory as a simulacrum rather than a simulation. And we were able to show that you could make a genetic map and physically pick the genotype and the phenotype for the droplets you wanted. And so this started to show us that not only could we create robotics that would run a programming language that is universal, but we could also start to do evolution in that. And maybe you can kind of see my mission coming through here of trying to make a robot that's literally going to brute force the origin of life one day. So one of the things we've also been trying to do is look at design of experiments in physical space with crystallization. There's a huge array of experiments going on here. Can we see crystallizations? And in my own lab in polyoxymetallate, I had a very fun argument with a referee years ago where I wrote a paper called Robots v Humans. I submitted it on April Fool's Day to Agavanta, but it took them some time before they actually sent it out for review. It wasn't a joke, it's just that obviously the robot wasn't competing with the human, but what we were able to show is that the robot was able to cover more space than the human because the robot had more freedom to make up its solutions, whereas the human would typically make up its solutions in order, changing the concentration rather than randomly making up a concentration. And what we were able to see is that the algorithm could cover a bigger crystallization space and the human or random. And actually the follow-up paper, which was collaborative teams of robots and humans, did much better than the robot v human, but it caused me some good fun with my team when we were discussing with the referee what that collaboration meant. I just want to show you a little bit how we're making a crystal hotel. This is kind of an extreme version of, but fits very nicely with the discussions we're having earlier about discovering new porous materials and how could you possibly cover enough space. And what we decided to do in my own lab was to see if we could build a system that would, by hand, this took 3 months to build a little crystal hotel that could do the synthesis of the clusters and the materials, and then basically put them into a hotel, a bit like one of these vertical car parks you might see in Japan, and then keep track of where all the materials are, so we could literally play around. This is a prototype. Occasionally it's temperamental when it throws the tray on the floor, which is comical to watch on video, but kind of distressing if you're the postdoc building the system. And you can see on the left-hand side the process that the system is going through. If I speed up a bit, you can see how the system is working, how we basically do the reactions in one wheel and then transfer them over into the trays. Okay, now I'm going to try and stop. I think I've got about 7 minutes left, and I want to stop in about 3 or 4 minutes to have time for questions. Is that correct? And then I think what I would like to do is just talk about discovery, because really I'm a discovery scientist and I do love doing manual chemistry, because I still dream occasionally I could go in the lab and discover something, or at least my postdocs and students. So, but what we wanted to do is to say, well, how could we remove bias in the discovery space? Could we combine liquid handling, automatic analysis and continuous reactivity assessment to do something that I wouldn't normally do? And I always say, you know, I'm a professional, I mean, idiot probably is a bit too harsh, but I'm professionally naive. And by being professionally naive, I can start in the part of the parameter space where the professional scientist might say, well, I've looked there before. Why are you looking there again? And I think that there's a lot of unconscious bias in the way we design our reactions. So what I wanted to do is to build a system whereby we could do a combinatorial chemistry, but not methyl, ethyl, butyl, futyl chemistry, but search reactivity first. So I wanted to look for unknown unknowns. And to do this, we made a scheduler that would react reagents together in a series of reactors and then assess what had happened using NMR. And we were able to add the NMR into the fume hood. We started this work about 6 years ago now. And we've gone a few generations of benchtop NMRs where we've got NMR, mass spec and infrared and some further chemistry kind of put together. What we were able to do is teach a neural network on the left-hand side here by a series of convolution, max pooling, reshaping and concatenating the data to basically train an algorithm to notice if a reaction had happened or not. And that I think is quite nice, because then what we could do is, if you go to the part on slide right on the right hand side, sorry for so much clutter, that you have this process where you randomly select some of the chemical space, you train the model, you predict the reactivity, you pick the most reactive combinations, and then you perform the reactions. And what we were able to do in this process, to cut a long story short, the punchline is gone from this slide, but to cut a long story short, we were able to discover a whole new range of reactivities and reactions that could not in principle be predicted by an organic chemist. So it's a bit like the uproar that AlphaGo Zero caused when AlphaGo Zero was able to beat a player at Go by making an unexpected move early on in the match. And what we've been able to do is show that if you take certain reagents, they will react together in a one-pot reaction cascade and do things you just couldn't predict beforehand. You just don't have the brain capacity to do it. And now whether that's useful or not is a debate that I'm going to be having with organic chemists and particularly people developing methodology for a long time, I guess. But it's a fun debate because, of course, it shouldn't be one competing with the other. It should be the AI system should be an aid for the expert chemist to search the chemical space. It's not a competition. things we've been doing in the lab is making the artificial material scientists and chemists, and this is kind of a broad overview of what we've been doing right now, which is basically exploring chemical space by having a surrogate model for some particular property and then generating molecules in silico. But here's the cool thing. Because we know how the KDL language works, we only play with molecules we know that we have the language to build on the computer. So we know that we are able to synthesize, in principle, these molecules. And that's very important if you're dreaming up new molecules from scratch. And this is something we're doing at the moment. And just a couple of examples here, how the protein encoder and the molecule encoder work together. Okay, I think I need to stop. It's been such a pleasure to visit, even though remotely, and I know we're all suffering from cabin fever, but I think that this is a really brilliant initiative, and I look forward to hopefully collaborating with people at the college, inspiring them, showing them not what to do or things like that, because we have a few of the bruises from the developing this approach. So the overall vision we have is Chemputation. It fits very well in the vision of DigiFAB, the autonomous discovery of new materials and molecules. We want to make sure it's platform universal. So this KDL that we're going to be releasing is not only we're releasing it open source, free for commercial use as well. So we're giving it away in the same way HTML has been given away. We don't see the point of redeveloping this, redeveloping the wheel. It's also task universal and it's chemical universal. I think I'm going to stop there just to say my lab are beginning moving into a new building in Glasgow in next year, which is called the digital chemistry theme. We have the top floor. We're going to be bringing in a load of other new groups to that. The digital chemistry vision is nothing less than programmable chemical materials science on demand. And so I can see there's a lot of synergy with what DigiFAB is doing. So I hope that we'll be able to use this occasion to overlap and to inspire each other and collaborate. I would love to thank my group. They're a brilliant bunch of people. I think the EPSRC in particular has really facilitated a lot of this by allowing me to have some background funding with a platform grant that to do projects that we wouldn't normally get funded under normal circumstances. So it's been a real privilege to have that. I will stop here and answer any questions, and thank you very much for inviting me.
So I was just saying, what would you say to people who ask about the difference between the computer that you talked about and some of these high throughput commercially available robots that's already available that will also allow you to explore reactions, you know, arguably on a nanoliter scale and stuff like that, right? In a very large quantity. What would you say to that?
Oh, I think they're totally different philosophies. I would say that the computer operating system will run these high throughput systems, and the computer system runs at high throughput now, has a high throughput add-on. The computer primarily was designed to aid the bench chemist, to basically remove bench labor from the fume hood at low cost, and then to have high throughput add-ons. And once we know that works, the problem with a lot of high throughput chemistry is that you tend to make known unknowns, i.e. you put together molecules you know are going to react. You don't do unknown unknowns, and you also don't make molecules that require a lot of very sophisticated unit operations, whereas a computer can do those sophisticated unit operations. So the ultimate dream is to have those combined together, and we have a high throughput version of the computer that brings together the synthesis of a valuable scaffold that you would do on, say, a gram scale, and then many hundreds, if not thousands, of reactions on the nanoliter scale in the high throughput add-on, the computer, because it all uses the same language. You know, have no vendor locking. And the problem with a lot of these high throughput systems is they are very expensive, and it's very difficult to verify what people have done. So I think they collaborate together nicely, and I would like to see there's too much vendor locking going on with these very expensive machines.
Thank you, Sophia.
Yeah, thank you, Mimi. Thank you, Lee, very much for your inspiring talk, and we also look forward to working together in the future as well, and hope you can actually visit us. It's my great honor and pleasure now to introduce our next speaker, Professor Donna Blackmon, who is joining us from San Diego. She is at the Scripps Research Institute. She has an endowed chair in chemistry, and she's also the department head of chemistry there as well. She's a chemical engineer and chemist, and she's in the National Academy of both of these entities in the US. And we are absolutely honored that she is at the chair of our external board and that she's agreed to talk to us today about vision for 2030 and opportunities for data-rich chemistry. Thank you, Donna, and over to you.
Okay, thank you very much, Sophia. Can you hear me? Is everything working? My slides are up? Okay, great. All right, well, thank you very much for the kind introduction, and I'm just delighted to be here to help launch DigiFAB. I think it's a tremendous effort, and we've seen already this morning from Sophia laying out the vision and from the absolutely stunning work going on in material science, combining computation and experiments at Imperial College already. It's just going to be wonderful to see what comes in the future. The title of my talk, I'll explain it about halfway through this Vision 2030, but I'll just note that that gives me about 10 years before Lee Cronin's computers take over. But what I'm going to do today is talk to you about my timeline in this area, how I got involved in what we call data-rich chemistry, and how things have developed. And it's going to be in the context of the pharma industry, because that's the area that I know, which is one aspect of what's going to be going on in DigiFAB. So to start out with, I'll just mention this timeline for the commercialization of a pharmaceutical product, which can take over a decade. Now, this timeline may be a little bit turned on its head, as we've seen in the last year with the development, at least for emergency use of COVID-19 vaccines. But typically, it's quite a long process, and chemistry gets involved in the very beginning in drug discovery, and then other people kind of take over in these trials. But then towards the end, when you're optimizing, finalizing the synthetic route and optimizing and scaling up the process is where chemists get involved again. And so time is of the essence. Time is money when the patent clock starts ticking. So anything that can help us get more information faster has always been of interest in the pharma industry. But it really goes back about 30 years where people started to think about what I call data-rich approaches. If you go back to about 1990, the big thing going on in pharma then was development of anti-HIV protease inhibitors. Many people listening here may be too young to remember this, but a diagnosis of HIV in the late 80s and early 90s was tantamount to a death sentence. We had some treatments, but there was a lot of resistance built up, and there was just really no way to treat these diseases until these protease inhibitors and then later got combined into the current cocktail drugs were developed. But in the early 90s, the first results from very early clinical trials were coming in. With Merck had one drug, this Crixivan, and others companies had similar versions. And the clinical trial results were just outstanding. It was just exhilarating to see how well these drugs were working. But people were excited, but they were also frightened. The pharma executives were very frightened because this was a huge volume drug. Patients had to take 3 grams a day of this drug. Someone at Merck told me they did a back of the envelope calculation and realized that if every Merck plant in the entire world did nothing but make Crixivan, they couldn't make enough of it. So for the first time, they actually got a little bit more worried about efficiency. Typically, when they would get the drive was to get a molecule online as soon as the patent clock, as early after the patent clock gets ticking as possible. And so efficiency in getting there wasn't as important as just getting there, because cost margins in the pharma industry would allow them to actually not worry so much about efficiency. But this was the first time where it actually mattered. And so one person at Merck, who I think was quite a visionary, had the idea, which sounds like a no-brainer, but that if we understood the reactions better, we might run them better. And so they decided to set up a lab, and they asked me to start this lab, which was called the Catalysis and Reaction Engineering Lab at Merck. And it was really the first effort there dedicated to not just to a certain drug molecule, an MK number, but to analyzing all the reactions, each reaction that came up, to try to make, to try to have it a much better process before they went to the pilot plant for clinical, to make the clinical materials, or eventually for manufacturing. And this was it seemed like a crazy thing to do at the time. I left a tenured academic position to start this lab. Everybody thought I was crazy. But it was a time of beginning of huge changes in the pharma industry. And I have to say that it was a defining experience of my career, the time I spent at Merck. So we worked a little bit on this Merck's Crixavan, and I've outlined the part of the molecule that I'll tell you about today, because I promised Mimi that I would have some kinetics in my talk, even though it's going to be a little bit more of a 30,000 foot talk. But the problem here was that we were doing this, we wanted to make the S-carboxamide, piperazine carboxamide, starting from the pyrazine. And the idea was to try to stop at this tetrahydro molecule so that we could then do a chiral reduction to get the S-carboxamide. And this was very early on. They didn't even have analytical for knowing what we were making in this reaction. And it's a very complicated molecule altogether. 5 chiral centers that all have to be enantiopure. So this was really the first time that Merck had an effort where we used in situ tools. Back in those days, people didn't have React IRs on their bench like the Rohr laboratory at Imperial. We were just getting these tools into my lab. And this was really one of the first demonstrations of the power of using really data-dense approaches and orthogonal approaches to a reaction. So we used React IR. We realized we could see the starting material going away, the product coming in, and we had one intermediate, which we didn't know what it was, and we didn't have analytical to tell what it was. So the question is this the tetrahydro or the dihydro? If it's the dihydro, we're in bad trouble, because that meant it would go rapidly from here all the way to the racemic product. But if it stops at the tetrahydro, we would have a chance to do the chiral reduction. So we were using not just the React IR, but we also were measuring hydrogen uptake, 1 molecule of hydrogen at each step. And we were measuring with reaction calorimetry the amount of heat released at each step. And you can calculate what that would be to get to the dihydro or to the tetrahydro. Oops, to the tetrahydro. And then you just put in the experimental results, and it turned out it was a tetrahydro. So that was a good day. And that was actually the experiment that really changed a lot of minds at Merck about this approach. You know, they didn't think they needed fancy chemical engineers telling them, trying to understand temporal changes. They were looking for a yield at the end of a reaction. You know, they were putting 16 par shakers with palladium carbon, coming back the next morning and finding, the final piperazine product each time. So this was really changed a lot of minds at Merck about the power, the enabling power of in situ tools like this. And it also let us build, with a kinetic model based on those results, a way to maximize the tetrahydro. So we could make mostly tetrahydro without losing much to the piperazine carboxamide, and then go on to the chiral reduction, which is what we did. So I just bring that up as an example because it really did sort of spark at Merck and other places a revolution in the development of these kinds of tools. Process analytical technology, or PAT tools, people talk about, both at Merck and across the pharma industry. And I would have to say eventually academia, although academia was later to the game than the pharma industry was, because I think that, time being money in pharma, it became much more of an urgent idea to try to make use of these tools. So then we go on to well, it took a little while actually for the FDA to come up to this, but now even the FDA has bought into the use of these tools for the approval process. When you get a drug approved, it's not just the drug that gets approved with the clinical trials with if it's safe and efficacious, but the process has to get approved. And it used to be that you'd make 3 batches and you'd show that unless it was Tuesday and a full moon, you could do it. But now it's much more scientific. You can turn in these PAT traces as part of your approval process. So it's called risk-based assessment based on process understanding, or it has its own acronym now of quality by design. So, a lot of things are changing over this time, and the realization that that data-rich approaches, the more you can learn about the reactions you're doing, the better off you're going to be. So the next sort of things that happened was a lot of the pharma scientists started to get really involved in this, and they got together in what they call pre-competitive collaborations to try to develop what they call enabling technologies for the pharmaceutical industry. And this was a meeting at the Council of Chemical Research with Chris Welsh at Merck, Joel Hawkins, whose name you'll hear again, at Pfizer, and Jean Tom at Bristol Myers Squibb. And they really started talking about what kinds of things that they could share, data and technology advances that would not take away anybody's IP, not talking about the particular molecule you're making, but help everybody make their molecules better. And that led into several other things that happened. I organized a workshop at the US National Science Foundation to talk about how can we enable and innovate the way we study chemical reactions through this data-rich approach. Mimi came and talked about things going on at Imperial at the time. We had people from academia, industry, and even government discussing this approach. And that was in 2014. And then a year later, another Council for Chemical Research meeting with the overall theme of disruption, and one of the sections was on biotechnology and process chemistry. And so again, people were talking about just looking back at the amazing changes that had already gone on, and trying to think about what's going to happen, what we can do in the future as we try to develop even more tools to really look inside reactions and find ways to get more data faster, which clearly includes automation and AI and machine learning. So the scientists who got together about this pre-competitive collaboration developed what they call the Enabling Technologies Consortium, and they're still working together on this. This came out in 2017, I think, talking about automation in the lab, both chemical reactors and crystallization, and analytical tools. Analytical is probably one of the biggest bottlenecks in pharma, and then so that really involves high throughput experimentation. So those efforts are ongoing, and the names on this paper come from about, I don't know, it's maybe half a dozen or more different pharma companies working together. So the next thing that would bring us up almost to the present day, earlier at the beginning of this year, the national academies decided they wanted to have a number of different discussions and end up writing a report that will be out later this summer on frontiers in chemical engineering. And so it covers lots of things more than just what I'm going to talk about, but it's the follow-on of a very famous report called the Amundsen report that was more than 30 years ago. But now, in updating that, what are the new things that we want to think about in chemical engineering? And it's all what we're talking about now: computer modeling and for design, machine learning and artificial intelligence, synthetic biology, and scalability. Scalability and sustainability are big things. So I was asked to speak on the subgroup of health and medicine about things going on in pharma. And it was great timing that this came up, because just before that, this is where the title of my talk comes from. Joel Hawkins, whose name you already heard, who's a scientist at Pfizer, had instigated this, what he calls Vision 2030, maybe not as far-reaching as we should be, but just was an idea to try to look ahead about what's going on in pharma. And so what he did was he set up a series of discussions by Zoom, of course, non-confidential, between academic and industrial scientists in chemistry and chemical engineering, trying to think about what are things going to look like in 10 years. So I was participating. This Lee Cronin was also one of the experts participating in these discussions. And the central question that was based around was, can we increase productivity tenfold, say, by 2030? Just a sort of a goal, just to try to make us think about what things we could do. And so if you have a central question, can we increase productivity? You probably want to be able to define productivity, which you can define in different ways. In pharma, it's usually defined as the efficiency in the design and the development of a process that will be scalable processes for making small molecule API, active pharmaceutical ingredients. And you could also apply this to the formulation steps that happen after that, which would be solid materials steps. If you're talking about lab work, you might define it in terms of how much lab space you use times how many calendar days for a particular project. And you also, in pharma, you can try to pinpoint the the bottlenecks. Where are things slowing down? You know, where do we, you know, what's our rate determining step in the whole drug development process? And it turns out from these discussions that it generally is not manufacturing itself. It's earlier steps, things like analytical and just getting the data. So I'm not going to go through everything that we talked about at those meetings, but I just want to highlight a few of the target areas, target issues for future development. And the discussions really do follow on from a blueprint that came up more than a decade ago, the 2007 ACS Pharmaceutical Roundtable, the ACS Green Chemistry Institute. They came up with key areas that would do better, could be improved to be more green. And these are chemical transformations that are of interest in pharma, organic chemistry reactions. And so greenness wasn't necessarily what the pharma was so interested in. Dave Lathbury, who was head of process research at AstraZeneca, used to say, green chemistry is just good chemistry. You know, if we do good chemistry, it will be greener than bad chemistry. So actually preceding this roundtable was something that actually also happened at Imperial. When I was there in it was about 2005, I think, I got together with the three heads of process chemistry, AstraZeneca, GSK, and Pfizer, brought them down to Imperial to talk about how we might collaborate. And we had a bunch of academic chemistry and chemical engineering faculty at Imperial joined in these discussions. And they just started, the pharma guys started writing on the board these things, these things that ended up on this wish list of the roundtable. And things like, you know, amide bond, we need to be able to make amide bonds. We need to be able to try to do coupling without using halides. And the academics were pretty stunned, actually, because most people had not had much contact with pharma industry. And it turns out we were often working on problems that were not of interest, like let's develop the 155th chiralphosphine ligand to hydrogenate enamides. But the discussions were quite fruitful, and it ended up in what became the PharmaCat consortium, where these three companies were the first three, but then it got expanded. They put in some seed money that could be seed money for projects at Imperial. And we stipulated in the beginning that it had to be a chemist and a chemical engineer working together to propose a project that could get funded by this. And you can see where that went. I mean, look at ROAR, look at the tremendous collaborations that have happened at Imperial since that time. So, you know, and that's then developed, you know, from PharmaCat into ROAR and now the Doctoral Training Center. So I think that instigation of that kind of collaboration was a huge boost, which is really going to be important, I think, going forward in DigiFAB. So some of the things we talked about is, you know, how do you drive these kinds of initiatives and how do you fund them? It looks like DigiFAB is on its way, has a good model for this, but these are the sorts of things, if we're going to make these initiatives work, we have to figure out how we're gonna do that. And then this really plays into also the need for creativity and innovation, which really means need for better interaction and crosstalk, not just between academia and industry, between chemists and chemical engineers. And now I think we need to bring in bioinformatics people. We need to bring in, you know, all the other disciplines that are going to be quite important for this kind of initiative in automation, machine learning, artificial intelligence. You know, really for the future way that we're going to develop, well, in this case, develop organic chemistry towards pharmaceuticals. So I'll just go over a couple of the issues that we came up with in these discussions. And one of the big ones is analytical challenge. That's one of the biggest pinch points in pharma, is just how do you, measuring what you think you're measuring and getting the right measurements and in the right time frame, you know, fast, dynamic measurements. And if you talk about automation, we talked about, you know, can we just keep improving what we're doing, or do we completely think outside the box and come up with entirely new tools? And that's part of the discussion I think that Lee Cronin was quite interested in. And also the next one, use of AI tools. In pharma, it's really important to think about processes being modular. It's very important to think about reactivity patterns and to try to develop predictive tools so that we can predict ahead of time what those reactivity patterns are going to be. And the last point, process robustness, is something that's really, really critical in pharma. You really need to talk about scale. scale transparency. You need to be able to understand that if something that you do in the lab, you need to be able to very quickly make it work in a pilot scale reactor and then, you know, on full scale. And so measurement here is also incredibly important. So those were some of the analytical challenges. Another challenge is data. And I love this. This is a TOC graphic from Tom Welton. Just came out a couple weeks ago, this paper in Chemical Science talking about machine learning algorithms for ionic liquid chemical space. But you could apply that same diagram to not just to ionic liquids, but to a lot of issues. You know, if we're only looking at the tip of the iceberg of what the available data is, you know, the machine learning is going to be hampered, is going to really be sort of handicapped by not knowing what's under the iceberg, and it could, you know, could end up being more than no problem. But so the problems with data, one thing is that the quality of data often is poor, and often in pharma people don't get temporal data. They get a yield or a selectivity at the end of the reaction, and they don't have any information about how it got there, which can be really critical to understanding what happened in the reaction. The other thing is people don't talk about what didn't work. You know, academics never publish failed reactions, but this is really critical to getting at the whole chemical space. If we don't know what didn't work, it's going to be really, really hard to figure out, you know, what will work. And so, and you're really going to need that kind of data for making AI work for you, because you want it to be predictive. You want to be able to understand reactivity patterns to make it predictive. And that means we don't want people to hide their failed reactions. And what was big in these discussions was the way that pharma companies, when they share in this pre-competitive way, they could just have mountains more data to look at than if they each looked at their own data sets. And so that's going to be that is already a big development in pharma, that they're being allowed to share this kind of data. And the other big point that comes up in terms of that, trying to share data, is standardization. You know, we just don't have standard ways of collecting data. And if we're going to be able to mine these data for AI and for machine learning, we really need to be able to put things in a standard way. So this is actually the end. I probably talked faster because I was a little worried about having enough time. But this is just a couple last points that came from Henry Dabina, who's the president and CEO of Mettler Autochem, and who's been big in this area for more than 3 decades about automation, lab automation, really mostly in the pharma industry and in academia. And he just has this graph that he made, and obviously we apply this to COVID, but it could be applied to any kind of an upset or a shutdown. Any kind of an upset causes you to have a downturn in productivity. And trying to think about coming out of that, like we are still now because of COVID, you have to plan for that recovery. And then you have to have a transition to whatever you're going to call the new normal. And what his graph tries to show is, you know, what people were doing before the upset. Whoops. And, you know, companies that were already employing these kinds of tools, were using automated tools prior to the shutdown, had much less of a dip in productivity, and they make it back to some new normal much faster. Companies that weren't using it ahead of time, but started to do it started to bring in automation during this planning phase, will have a lag, but they'll still get up to a pretty good productivity level at whatever the new normal will be. But companies that are making no investment at all in automation are probably never going to get back up to you know, the same relative productivity before such a huge shutdown. And so he actually showed, and it's you know, I'm allowed, it's not a confidential slide, but it comes from Merck as an example of this. This is, you know, building experimental efficiency. It's hard to see the slides, but these are years, okay? 2015, 16, 17, 18, 19, 20, okay? And up here is numbers of experiments conducted, and they color code them by different projects, probably different MK numbers for different drugs that they're working on. And it's really quite interesting. You think this is the shutdown, you know, for COVID. And look what happened after, you know, now actually going on as of October of last year. They almost didn't miss a beat at Merck because they had invested heavily in these kinds of tools. And you see papers coming out from Merck on on just not just automation. I mean, they were the first really that looked into this for asymmetric hydrogenation. The Januvia process, the type 2 diabetes drug sitagliptin. They won a green chemistry award in the US and also an iChemie award in the UK for an asymmetric hydrogenation process. And then they won another green chemistry award for a process that beat that one out, which is a biocatalysis process. So they won a total of 3 green chemistry awards for the same process. And a lot of it involved, the development in all those cases involved a lot of automated experiments. So so this is sort of the moral of the story, that if you invest in these kinds of tools, you will minimize, the effects of a terrible shutdown like what we had last year. Okay, so that's all I wanted to say, except for one thing. Oh wait, I'll just summarize what I was saying. Is it really looks like if you look at the last 30 years, this was really inspired by this huge critical epidemic of AIDS. The need to develop this in industry. I'm not sure that it would have happened as quickly if we hadn't had such a terrible need, and it became really a huge success story. And so everybody started developing these tools, and they ended up also in academia shortly after. And I consulted with several pharma companies to develop the same kind of lab that I had started at Merck, at Pfizer, and at AstraZeneca. And then now we're in a sort of a phase where we're trying to think about what's going to happen in the future. We're developing these enabling technologies. We're trying to work together so that all the data out there can be brought together for these to be put into these strategies for innovating through things, not just automation, but bringing in machine learning and AI tools to really mine what we have in our data. And so that was what led to what they're calling Vision 2030. I think it will go on beyond that, but just the idea that we're we're looking to see what the next 10 years are going to look like. So like I said, that's all I wanted to say, but I want to take 1 minute here at the end to recognize someone who is a giant in this field, and that's John Martin. John Martin was the CEO and president of Gilead Sciences. He retired last year, but he's the man almost singularly is responsible for saving millions of lives with his development of the HIV drugs. And then after that, cured HCV. I mean, he was just a visionary leader, amazingly creative and innovative. And he died very suddenly, unexpectedly in March, at the end of March this year. He had retired and was now serving on our board of trustees. And I don't know if you caught it on my title slide, but he endowed a chair at Scripps, which I am now the John C. Martin Endowed Chair in Chemistry. So I just want to take a moment to remember him, and also just to mention that he actually had degrees in chemistry and chemical engineering, which I think added to the whole creativity that he was able to bring to this field. So that's everything I was going to say. And I'm very happy to stop now and answer any questions. Am I now no longer, I have to stop sharing, right?
That's brilliant, Donna. That's a really good talk. So I have a question. So talking about— Am
I still sharing? Can I tell you? Oh, am I done? Have I stopped sharing?
Yeah.
Okay. Great.
So can you hear me, Donna?
Yeah. Yeah, I can hear you.
So the question is, if I'm going to ask you, if time and money is not a constraint, what would be a perfect process analytical tool that allow you to gather as the perfect data, if such a thing? What is the ideal data analytical tool for that?
Well, I mean, it may still be yet to be developed. That was one of the things we talked about. Do we need completely new tools? I think the components that go into a perfect tool would be, maybe it's more than one tool, because I think one thing that's critical is to have orthogonal ways to look at a system, especially chemical reactivity, because you look at, IR tells you something about the chemistry, the bond vibrations of the molecules. You can use all these tools can help you monitor temporally, monitor a reaction. But if you're monitoring orthogonal, we monitor looking at the CO bond change, looking at the heat developed, looking at the hydrogen taken up. that tells you 3 different things about the reaction. And if they tell you the same thing is going on, you have a lot more confidence in the tool. So I would say that automation, orthogonality, and dynamics of getting a lot of data fast so that we can look at fast reactions. So rather than say one tool, just those are the components that I think would need to go in. And I'm a big fan of temporal modeling. I just reviewed a paper. I'm sure it will be accepted. It's a really good paper talking about machine learning and bringing it in, but they didn't mention the word time at all. The only time it came up was talking about a timeline, and I think that not knowing how you got there to the end point of the reaction can cost you a lot if you don't have that information.
A whole new different question about how you then map the different temporal orthogonal tools onto the same timescale. But yeah, that's very interesting discussion.
Yeah, but I mean, if you think about all the tools that we've been using, you make a Hammett plot and you plot, relative rates or relative rate constants, and those two can be very different things. If you don't actually, you need to know the actual form of the rate law, the rate expression, to know if you're actually measuring apples and oranges when you compare 2 different reactions. Just a very simple example of how time, is quite important.
Thank you, Sophia.
Yeah, on that note, I'd like to thank Donna, and actually we do have a method now to put together trajectories of different times and use the right machine learning to scale that. So maybe we should.
Fantastic. Yeah.
And I do have to thank you, and thank you for, if I may be allowed a personal note in this day. When was it, 15 years ago, when you joined our department, and I was developing all these new mathematics, and I had to go exile myself to the Institute of Mathematical Sciences. You said to me, this is really important for chemistry, and a lot of people were not yet sure. And now all these methods are really, really popular, I think, or people may not know about them, but they're really there. And thank you for that inspiration personally, but also on behalf of everyone, thank you for your talk as well. And with that, I would like to introduce our head of department in chemistry, Professor Oscar Sess, who will close this meeting. I think Oscar is the architect of a lot of visionary activities in the department, and I will let him summarize our day for us. Thank you.
Thanks, Sophia. Can you hear me okay?
Yes, we can.
Brilliant. Hey folks, so as Sophia said, my name is Oscar Sess. I'm the current head of the chemistry department, and it comes to me to make a few kind of closing remarks. I hope you've enjoyed today's event. I thought it's been thoroughly stimulating, and I think that's in the main due to the actual kind of speakers we had today. I think, Ian, Sophia, Becky, Kim, Alex, Lee, Donna, I think they did a fantastic job of kind of showing just how critical this field is in addressing current bottlenecks, but also it is the beginning of a journey. I think, to say this will be finished in 10 years time, I think it's the beginning of a long kind of process. As well as thanking the speakers, I wanted to thank the team behind DigiFAB. A few of them have had the chance to speak today, but it's actually, I think the magic of DigiFAB is it really is a cross-departmental, cross-faculty initiative that kind of reaches out both in the college and beyond that. As Lee mentioned, we're looking to collaborate not just here at Imperial, but externally. But the people who spoke today are a key component of a much larger team that, in a very short period of time, has taken DigiFAB from a concept to a really kind of thriving kind of venture. And the last entity I'd like to thank is the college. I mean, we've actually got here today with DigiFAB because they kind of took a punt on us in terms of a vision we had about 8 or 9 years ago that started with my predecessors, actually. So Richard Templer, Tom Walton, and then Alan Armstrong really had, got us all thinking as chemists and molecular scientists about what was the future for kind of chemistry, not in 5 years and 10 years, but in 25 and 50 years time. And we actually went through a massive horizon scanning exercise about just over a decade ago. It took 2 years. Whole department was involved, stakeholders, about 80 external partners, really examining closely what the future of chemistry would look like. And it was very clear that, bottom-up led blue skies discovery was going to be pivotal, but there are also a plethora of challenges we came up with at the time, about 20 to 25, and that included digital chemistry and kind of digital molecular manufacturing. And what was really clear was that every challenge we came up with required chemistry at the centre, but working really, really closely with the disciplines in a seamless kind of way. Mathematics, life sciences, physics, materials, engineering, chemical engineering, you name it. And at the time, our infrastructure and our ways of working weren't aligned with that. So we went through a big process of kind of asking ourselves what we needed, new ways, co-location, new collaboration kind of models, embracing external factors such as Industry 4.0, the need to train new kind of graduates in new skills. And we put this vision to college, you know, and it was really about kind of reinventing chemistry from the bottom up. And chemistry, you know, the college really kind of supported us. I think it was a serendipitous time for us because at the same time, you heard Ian and others mention today, the college embarked on one of its probably largest ventures in history with the opening of the White City campus. And the vision for that was co-location of industry, academia, local community at scale. And when we put forward our vision for what we thought chemistry should be, it was strongly in line with that. And it was kind of, you know, fitting in the same way that chemistry was the first pillar of college back at South Ken. It actually became the first department to move with its partners over to White City. So college made, you know, a really probably one of the largest investments in chemistry in recent times. And it allowed us to move to White City. So we moved lock, stock and barrel research to Molecular Sciences Research Hub. And that's allowed us to kind of, you know, if you ever, we'd love to have you in our labs and show you around when things are slightly more back to normal, but it's a fantastic environment to collaborate. You know, it's not just chemistry in the building, it's chemistry with a plethora of other disciplines working together and kind of challenges that require multidisciplinary approaches. All our facilities are shared, both with internal partners and external partners. And that's a critical pillar, for example, to DigiFAB. The fact that all the elements we need for DigiFAB are in co-located spaces, either proximally or across the campus. What we also have now, which again did not happen before, is we have literally of the order of hundreds of SMEs and industrial partners on our doorstep. You know, we work more broadly with industry who are not geographic co-located, but actually having industry in our spaces across the road, in the buildings around us, it really means that the opportunities for translation are enormous, and that's something we're embracing as well. An example, for example, is cluster marketing I've put there. So a lot of the equipment you've heard about in DigiFAB, either stuff that we've made commercially or that we're developing bespoke, through partners such as Cluster Market, who we met serendipitously here because they're in the building next door. We kind of allow external users to get access to our equipment. The other thing is, you know, you heard from Sophia, and access to talent is a massive, massive deal. So, you know, we've had support both from the college and the EPSSC in setting up a number of kind of doctoral programs to allow us to train that next generation of scientists, the kind of scientists who understands the chemistry and molecular science side of things, as well as the engineering and the data analysis components. And, you know, we're going to supercharge that this coming October with the MSc in digital chemistry. And in addition to that is, you know, the other piece of support we have from college and the EPC was actually in terms of infrastructure. You know, we're really lucky to have RAW, which is a kind of key pillar of DigiFAB. That builds upon other initiatives in college, such as the Centre for Process Systems Engineering. And they give us access to really, really cutting edge, you know, commercial instrumentation. But as you saw from Lee's talk, the other flip side to DigiFAB and also what our collaborators are doing is building equipment from the bottom up, not relying on what is commercially out there. And a key element to that, which we have at White City, is the College Advanced Hack Space, one of the largest hack spaces in the world. And, you know, we're seeing a breadth of technologies emerging there from DigiFAB. And what we also want to see and hope to see down the line is, as well as collaborating with industrial partners, is this new generation of leaders that we're training, that they themselves will actually create the new set of spin outs that are going to push this kind of area forwards. And with that, I just want to say it's the beginning of a journey. It's a really exciting one. And at the heart of it is collaboration. So we'd love to hear from you. You know, DigiFAB, it's about working across disciplines to kind of achieve the aims of digital molecular manufacturing. I hope you've enjoyed today's event, and we hope to hear from you soon. Take care.